Okay, again, we have a big, long problem. We have to make sure that we can sort through everything here. So read it completely through. Same on the exam. You gotta, I know it slows you down, but you gotta figure out what you're after. Consider the reaction given there. It takes place at 355 Kelvin. That's not unusual to have the temperature there. We need to know the temperature because that'll tell us what Kc is for this reaction. A 2-liter vessel contains 3.15 moles of CO and 3.15 moles of H2O. Having the same moles should tell you something. And then I look at this reaction, I see it's 1 to 1. I wrote this up a while ago, so I see 1 to 1. That should tell you what the problem is if you've done enough of these. Now, if this is first time, of course you don't know what's going on yet, but that tells me a great deal that these two numbers are the same. How many moles of each species are present at equilibrium? Let me see. Yeah. At equilibrium if Kc equals 4.63 at that temperature. And so, write out the equation. I'm going to leave off the units, or the phases. They're given above. Now, they want to know how many moles of each species are present. They've just told us that they put this into a reaction vessel at the beginning of the reaction. But they didn't say anything else, so it must be an ice table problem because we just don't have enough information. If you're ever in doubt, just throw it into an ice table equation, or into the ice table, and see what you come up with. Now it's 3.15 moles in a 2-liter vessel, so 3.15 divided by 2 is 1.58 molar, and this is 1.58 molar. If we're going to deal with Kc, we need to be in terms of concentration. You can certainly put moles in here if you want, but when you get done, you're going to have to convert to moles per liter, and you'll see that because once you've filled in the ice table, you'll see that you're missing. You have well, you'll have x that you have to solve for, and the only way to solve for x is to use the Kc expression. So I know it seems like there's a million things that you can do here, but if you just read carefully, you're going to see that it all comes out. There's only one way to solve the problem, I should say. They don't say anything about CO2 or H2, so we know those are 0. I'll get here and I'm going to leave off the molars because we know what they are. Now, we have x. We can see that if we can solve for x, we'll have all the information, which means that since we're at equilibrium, if we can put them into the Kc expression, we should be able to solve for x, but only if we know what Kc is. So look back here. Yep, we can solve for it because we know what Kc is. So Kc and it does, I suppose, look like I'm kind of making it up. Oh yeah, he says that it can be solved because he knows. Actually, I didn't know because I was had a suspicion. But yeah, I should actually get my cheat sheet out here to make sure I get the right value at the end. But I wanted to just go through to show you what we're after. Yeah, so I do have the answer, but it wasn't. But you can certainly use the ice table to determine what you know and what you don't know, and how to approach the problem from there. Now, when these values are the same, and it's 1 to 1, you're going to find that you have an equation that contains an x squared term. Dang! If you have to solve for x and you have a term that's x squared, that means you have to use the quadratic formula. You have no choice. It has to be the quadratic formula, unless you have a system like this. Now notice, the top is x squared. The bottom is an argument squared. So if we take the square root of both sides, you have to do it to both sides, then you end up with x, 1.58 minus x, and then you have 4.63. It's 2.15. And then you can, now it's just x, not x squared. So now you can solve for it. You do x. I can do it out, 2.15 times 1.58. This is 3.4 minus 2.15x. And then this would be 3.15x is equal to 3.4. I might be off the page, but I'll be back on there in a second. 3.4 divided by 3.15. And this comes up to be 1.08 molar. Let me get back on here. So we solve for that, and then that is going to be the concentration of the CO2 and the H2, and then the concentration of the CO and the concentration of H2O will be 1.58 minus 1.08, so this is 0.5 molar. So now we know the concentrations of everything, but they want to know the moles. So we have to take the moles of CO2 equal the concentration, which is 1.08 moles per liter, times the liters. And what were the liters? 2. So this is going to be 2.16 moles. And that's also going to be the moles of hydrogen. And I'll tabulate this in a second. And then the moles of CO will be 0.5 moles per liter times liters, and we end up with 1 mole, which is also going to be the moles of, what's the other one? Water. So once we find the concentrations, then you just have to divide. You have to multiply by the volume of the container. So let me just rewrite it here. Moles of CO2 equals 2.16 moles of, I don't have to put units because I'm specifying what it is here, moles of hydrogen is going to be the same thing. Moles of CO will be 1, and the moles of water will be 1. This is unusual to ask for moles at this stage of the game, but I did it just so that we had something different. So usually you'll be just asked to find the concentrations, and I think that's what I do on the next one. So let's try that one. Consider this reaction. It takes place, notice the same moles, same number of moles for the two reactants. That tells you something it's very symmetrical, so there might be something to that. What are the concentrations of each species? Not the moles, the concentrations. It's the thing that can get students on the exam, because I may be asking for moles, I may be asking for concentration, just be careful. And then we have the ice table. Initially we have 1.17 divided by 3.35, so 1.17 moles divided by 3.35 liters gives us 0.349. Let me get my cheat sheet out here so I can just make sure I'm got the right numbers. Save me from making some mistakes here. And then now the change is minus x plus 2x. Got to get that. And then we have 0.349 minus x, 0.349 minus x, 2x. Now, we go back to the table, or back to the problem. You say, well, if we know what x is, we can solve for Kc. Well, they gave us Kc, so that's not what we're solving for. We're not. So these x's are what we're after. So odds are we have to take these values at equilibrium, put them into the equilibrium constant expression, solve for x, and since they want concentrations, then we're done. Once we find x, we plug it into these values, and we're there. So Kc is ClF2 over F2 Cl2 is equal to 1.97. Got that. And then ClF2, so we put in our values. We have 2x squared over 0.349 minus x. And there's two of them together. These are both the same, so we're just going to square it, save ourselves a little time. And this is 1.97. Okay, so you see this, and this is going to be 4x squared. You say, oh no, the quadratic formula. Well, the quadratic formula is going to come up. We're going to have to use it at one time or another. But here we don't have to. We just take the square root, like so. And then we have 2x, 0.349 minus x. We have 1.79 or 1.97. Take the square root. This is 1.4, and then we solve for x here. I'm going to do this relatively quickly. So 0.349 times 1.4, And as I've said before, if this is throwing you off, if because I'm not writing every step down is throwing you off, you have to come and see me or see your instructor, because this is math, a level of math you should be at. This shouldn't throw you. I should just say solve for x here and you should be able to get it. If you can't, you got a little work to do. So x is 0.144 molar. But that's not the answer. We want 2x and we want 0.349 minus x. So we solve, so this is going to be 0.288 molar. That is going to be the concentration of the CLF. I'm not going to go any further with that. Just writing these values below here should be good enough. And then we have 0.349 minus 0.144, and this is 0.205 for chlorine and 0.205 for the fluorine. So these are the concentrations for these species. I think that's all they wanted, right? Yep. That is the deal.